This section is about changing variables. This is kind of the big brother or the two-dimensional analog of U substitution. In order to do that, we're going to have to calculate something called the Jacobian. Let's think back to how we do substitution for single variable integrals. We have a substitution rule that lets us change the variable of integration. When we change the variable of integration, that allows us to substitute out a variable in the function, but it also requires us to do two things as well. The first is that we have to change the bounds of integration. So for instance, here we have the area of a circle function. We don't know an antiderivative of the square root of 1 minus x squared, and so we do the substitution x equals sine of u. The first thing that changes is it allows us to plug in sine of u for x squared, and 1 minus sine squared is equal to cosine squared, which makes the algebra doable. But the other thing that changes are the bounds of integration. On the left here, we have the integral of this function from -1 to 1, but once we plug in x equals sine of u, as x goes from -1 to 1, as u goes from negative pi over 2 to pi over 2, so our bounds of integration change. But one other thing has to change as well. And you'll notice I've broken these integrals down into the rectangles that approximate them. If we have a set of regular rectangles here, all of the same base, then when we do this substitution, changing our variable from x to sine of u stretches out the base of some of these rectangles. If we don't account for that stretch, then the area of these rectangles, and hence the area representing our entire integral, will be incorrect. And thus, whenever we do a substitution, the third thing we need to substitute is the differential. Specifically, we replace dx with cosine of u du. The question is, how do we do that for a two-variable or more variable function? Instead of the Cartesian coordinate system, that is the xy coordinate system, we're going to be using other coordinate systems for the plane when it's convenient. Here's an example of an alternate coordinate system. This is called the parabolic coordinate system. Instead of vertical lines and horizontal lines being the grid lines, here the grid lines are parabolas. The upward-facing parabolas give you your sigma coordinate, and so here's sigma equals 0, 1, 2, and 3. The downward-facing blue parabolas give you your tau coordinates. So here's tau equals 0, 1, 2, 3. So the point as marked here is on the sigma equals 2 and the tau equals 3. In terms of the sigma and tau coordinate system, that is the point 2, 3. I will note that this is not a particularly useful coordinate system. We're going to use this to learn how coordinate systems work, but there's no reason to memorize this, and we will never actually convert to this coordinate system in order to solve an integral. Now, in order to practice with this useless coordinate system, we will need some formulas that will allow us to convert from sigma tau coordinates back into the xy coordinate plane. And here are those formulas. The x-coordinate of the point sigma tau is just sigma times tau. The y-coordinate of the point sigma tau is 1/2 tau squared minus sigma squared. We can actually express this if we want as a function. I've used the letter r here, and so r takes the point sigma tau, and it outputs the point sigma tau, comma, 1/2 tau squared minus sigma squared. I've just put the x and y coordinates together there. You'll notice, though, that I've actually written this as a vector, for reasons that we'll go into later. So if I wanted to convert a function in terms of xy into a function of sigma tau, that would not be very difficult. Wherever I see an x, I can replace it with sigma tau. Whenever I see a y, I can replace it with 1/2 tau squared minus sigma squared. So that part of replacement is straightforward. But that still leaves plenty of questions about how we would integrate a function in terms of sigma and tau coordinates. Here's the problem. If you want to integrate in terms of sigma and tau a function f of sigma tau dA, then you would integrate this, at least most conveniently, over small rectangles delta sigma by delta tau. But what do those rectangles actually look like? Well, they look something like this diagram here, where starting at the point 2, 3, I've traveled delta sigma in the sigma direction and delta tau in the tau direction, and I've actually followed the grid lines to see what that rectangle looks like in terms of xy coordinates, and it is this slightly curvy shape. It'd be fairly difficult to calculate the area of these things, and even harder to work them into a formula in a general way. But this is what we would need to do in order to calculate dA in terms of sigma and tau. Fortunately, there is a solution. Traveling delta sigma in the sigma direction, or delta tau in the tau direction, leads to a very ugly shape, which is hard to calculate. So instead, what I'll do is I will fix a particular direction. That is, I'll go to the point 2, 3, and I will travel delta sigma in one direction from that point. And the direction that I will choose is the partial derivative of the function r with respect to sigma. So I will ask the question, how does the x-coordinate change as sigma changes at the point 2, 3? And how does the y-coordinate change as sigma changes at the point 2, 3? And I'll put those changes together to get r sub sigma, the partial derivative of the vector function. And now we see why we needed a vector function. Because in order to take a derivative, you have to be able to subtract, and you can subtract vectors, but you can't subtract points. And so that's what I have here. I've gone r sub sigma, and I've gone delta sigma times that vector. And I've also gone r sub tau. I've taken the tau partial derivative of the vector function in order to get a derivative vector, and I'm going to go delta tau times that vector rather than going delta tau along the coordinate system, which is much more difficult to measure. Okay, so I've taken this r sub sigma delta sigma and this r sub tau delta tau, and now I have some sort of parallelogram. I like parallelograms, but as you can see, the parallelogram that I've measured is actually quite different from the actual shape that you get when you travel sigma and tau in this coordinate system. We're going to fall back, though, to our standard argument in calculus that says these things may be different, but as delta sigma and delta tau get smaller, the difference becomes smaller and smaller. And in fact, for sufficiently small sigma and tau, the area of this parallelogram dA becomes an arbitrarily close approximation of the sigma tau rectangle, or quote rectangle, that we had before. Since integrals are predicated upon the idea that we are dividing into smaller and smaller rectangles anyway, that means that for the purpose of calculating the limit, we can use these parallelograms instead of the sigma by tau funny-shaped rectangles. And so just like in an integral, when delta sigma and delta tau get small, I'll replace those by d sigma and d tau. And then all I need to do is figure out what the area of this parallelogram, whose area is dA, what that area is. Well, long ago, I gave you an application of the determinant, which is that if you have the determinant of two vectors, that is the area of the parallelogram spanned by those vectors, or in the case of three vectors, it's the volume of the parallelepiped. And so, by distributing d sigma across the coordinates of that partial derivative r sigma, so dx d sigma and dy d sigma, I have my first vector in the first row, and by distributing d tau across r tau, I have the vector in the second row. All I have to do is take the determinant of this 2 by 2 matrix, and that gives me an expression for dA. So let's go ahead and compute what dA would be for parabolic coordinates. So the formula we had is that dA is the determinant of the matrix, dx d sigma times d sigma plus, or excuse me, not plus, comma, dy d sigma times d sigma over dx d tau times d tau dy d tau times d tau. So those are the two vectors, and we're just going to find this determinant. Let's calculate these partial derivatives using the formula we have up above. So dx d sigma is tau. dy d sigma is negative sigma. Dx d tau is sigma d tau. And dy d tau is tau. And then we have a d tau. We'll take this determinant, and we're going to get tau squared d sigma d tau for the first diagonal, and then for the other diagonal, which should be a negative, so we're going to have minus a minus sigma squared d sigma d tau. And notice that the d sigma d tau could factor out of this. In fact, it will always be able to factor out of this, or it will always be able to factor out of any similar computation. And we can write that this is equal to tau squared plus sigma squared d sigma d tau. Let's express what we've been doing here in general. So given a general coordinate system, u and v, we're going to call the determinant dxy over duv to be the determinant partial derivative of x with respect to u, partial derivative of x with respect to v, partial derivative of y with respect to u, partial derivative y with respect to v. Why have we gotten rid of the du and dv? Well, because those are always going to multiply together and can be factored out. So this determinant is called the Jacobian, and it has the property that whenever we see dx dy, or for that matter dA, that can be replaced by this determinant times du dv, that being the du and dv that we would have factored out. We can define the Jacobian similarly for a 3-variable coordinate system. We would need 3 variables, and we would need 3 vectors, and we would be taking a 3×3 determinant. So over the next few classes, we will be using the Jacobian on actually useful coordinate changes. But in order to be ready for that, you should be able to understand what the Jacobian did, and you should think back to substitution and ask, what 3 steps are we going to have to follow when we rewrite an integral in terms of a new coordinate system?